In this video, I am explaining bivariate discrete random variables, their probability function and distribution function. In previous video, I had already explained what are discrete random variables, how to denote discrete random variables by these capital letters X, Y, Z. Now, this discrete random variable takes only whole number as its value, and these values can be arranged in the form of sequence. Discrete random variable has its probability distribution in the form of probability mass function, which is denoted as p of x at the value xi as p of xi, and the conditions are each probability value must be greater than or equal to 0 and sum of all probabilities must be equal to 1. This is the probability mass function of the discrete random variable. Then we have seen the distribution function, which is denoted as f of x. It gives you sum of all probabilities up to x including x, that is cumulative distribution function. So if you have the probability distribution in this form x p of x, x1 p1 x2 probability value p2 and so on, then the distribution function f of x is obtained by adding these frequencies. First p1, then p1 plus p2, next for x3 f of x is p1 plus p2 plus p3 and so on. This is about the distribution function. All this is related to one dimensional discrete random variable. But there are situations where we have to study two dimensional random variable in connection with a random experiment. Say, for example, suppose we may be interested in recording the number of boys and girls born in a hospital on a particular day. So here in this case, there are two random variables. One corresponds to number of boys born in a hospital, another corresponds to number of girls born in a hospital. So x you can name it as number of boys, another random variable y as number of girls. Then x can take 0 1 2 3 and so on, these values. Y can also take 0 1 2 3 and so on. So you need to study these kind of variables. These kind of variables are called as bivariate discrete random variables. Discrete because they are taking only whole number as values and you can arrange the values in a sequence form. Bivariate because with the same experiment here, two random variables are associated. That is the need of studying bivariate discrete random variable. So now definition of bivariate discrete random variable goes like this. Let x and y be two discrete random variables defined on the same sample space S of a random experiment. Then the function, that is ordered pair together capital X comma y defined on S, is two dimensional because it has two random variables. Each value of x and y is represented as x comma y. It is in the same way, instead of one variable, now here you have two variables x and y. Each value of x and y is represented as ordered pair x comma y. You can add indexes also. When you have more values for the random variables, you can state it's xi comma yj. I index is for the first variable and j index is for the second variable. So that is how to define a bivariate discrete random variable. Now, after defining this, you have to get its probability distribution. So, same as this, it is probability mass function for a one dimensional discrete random variable. But in a two dimensional discrete random variable, the probability mass function is of three categories. One is joint probability mass function, another is marginal probability mass function, and conditional probability mass function. Here there was only one probability mass function, but in this case, as there are two different random variables, we will have three category of probability mass function. Let us see what are these one by one by considering an example. Here, I'll consider a simple random experiment of rolling a die once. So when you roll a die once, you will have six possible outcomes 1, 2, 3, 4, 5, 6. Now, if we are interested in finding the probability of or probability distribution of number of times odd number and number of times prime number appears when you roll a die once, if you want to calculate that, then let us see how to do that. Now, when you look at this requirement, you can see there are two discrete random variables. One is getting number of times odd number appears, and another random variable is number of times prime number appears on a die when you roll a die. So x can take how many values? This is a bivariate random variable associated with the same random experiment. So x can take 0 and 1. These are the two values. Number of times odd number appears. How many times odd numbers appear when you roll a die once? Either it appears or it does not appear. That means if you get 1, how many odd numbers? One odd number. If you get 2 when you roll a die, then it is not an odd number. So there is no odd number, means it is 0. So x is a random variable which takes two values 0, 1. Similarly, in this case also, number of times prime number appears. Either it appears or it does not appear. If it appears, the value of random variable is 1. If it does not appear, value of random variable is 0. So x takes two values 0, 1, y takes two values 0, 1. Now I have to get the probability distribution of this bivariate discrete random variable. So you have to remember these things for an experiment here. Odd numbers are 1, 3, 5 and prime numbers are 2, 3, 5. So you have to write a table now. Earlier you had a simple table where x p of x because one dimensional. Now here it is two dimensional, two variables x and y. These values, below values, will give you the values of the random variable x, and these values will give you the value of the random variable y. So 0, 1, 0, 1, you write it. Now 0, 0, you have to get the probability distribution when x is 0, y is 0. So when x is 0, y is 0 means no odd number, no prime number appears. So these are odd and prime. Which are the remaining outcomes? 4 and 6. How many favorable outcomes? 2. So it is 2 by total outcomes 6. So you will get 2 by 6. Then 0, 1. No odd number, one prime number appears. So no odd number means possibilities are 2, 4, 6, out of which prime number is 2. Okay, only 2 is prime. Therefore, one possibility 1 by 6. Then one odd number and 0 prime number. Odd number appears, prime number does not appear. So, odd number appears means 1, 3, 5. Prime number does not appear. Out of these 1, 3, 5, 3, 5 are prime. So, leave them. So, 1 is neither prime nor composite. Therefore, 1 by 6. Then 1, 1 means odd number appears as well as prime number appears. Which numbers are both odd and prime? Odd number appears means 1, 3, 5. Out of 1, 3, 5, prime numbers are 3 and 5. So, two favorable outcomes by 6. Therefore, now you have to find the total row sum here. 2 plus 1, 3 by 6 means 1 by 2. This is also 3 by 6 means 1 by 2. Here column sum 3 by 6 is 1 by 2. This is also 1 by 2. So when you add up all these values, you will get 1. Here half plus half, this is 1. Here also this row sum equal to 1. So this probability distribution is called as the joint probability distribution, and the corresponding function is called as joint probability mass function. Joint distribution because this gives you the joint probability when x and y two discrete variables corresponding to those two discrete variable values, we will get the probability distributions. Now, to represent joint probability mass function, we are writing here P of x equal to xi, comma y equal to yj. J is the index of the random variable y and I is the index of the random variable x. That is, here this value is x1, y1. First row, first column. This is x1, y2. First row, second column. x2, y1, then x2, y2. Second row, second column. Like that. So, joint probability mass function, earlier you had just p of x equal to xi because one dimension. Now p of x equal to xi comma y equal to yj, which is represented as p of xi comma yj. This is your probability mass function. Now conditions are, here you had all probability values should be greater than or equal to 0. In this case, that is true, but xi comma yj you have to write p of xi comma yj greater than or equal to 0. And second condition is summation over I summation over j p of xi comma yj must be equal to 1. That is, this sum as well as this sum both must be equal to the value 1. Then this is called as joint probability mass function of the variables x and y. Now about marginal probability mass function. So it is the probability distribution of x or probability distribution of y individually. This was all both together. Now here you have to find out probability distributions of x and probability distribution of y individually, separately. Then such distribution is called as marginal probability mass function. See, now if you want to get probability distribution of the variable x, then we have to get the row total because x values are here 0, 1. So you have to get the total of first row, total of second row. That is already we obtained here. So which is denoted as p of xi summation over j because row is fixed, only column changes. When you take x equal to 0, this row is fixed, you are just changing the columns. 2 by 6 plus 1 by 6, that gives you 3 by 6, which is nothing but 1 by 2. That's why p of xi comma yj summation over j, you have to take the row sum. So that is called as marginal probability mass function of the variable x. So in this case, it is obtained as x is the random variable. Its probability is p of x. The table you have to write, x takes the values 0, 1. So what is the probability corresponding to 0? Add these two, you will get 1 by 2, and probability corresponding to this 1 by 6 plus 2 by 6, that also 1 by 2. So now this probability distribution is called as marginal probability distribution of the random variable x. So that is the individual probability distribution. Now similarly, probability distribution of y is nothing but column total, which is denoted as pyj, that is summation of p of xi comma yj over I. You have to change the rows now. See here. Now if you want to get the marginal probability distribution of the variable y takes the values 0, 1. So here you have y p of y. Now you have to take the column totals. So this is the first column, second column. So y values are 0, 1. Column totals 2 by 6 plus 1 by 6, that is 1 by 2. Then similarly 1 by 6 plus 2 by 6, that is also 1 by 2. So this distribution is called as marginal distribution of the random variable y. This was the joint probability distribution. If you take the probability distribution individually, then that is called as marginal distribution. Now one more distribution is conditional probability mass function or conditional distribution. So conditional distribution is with respect to the concept of conditional probability. We have already seen what is conditional probability and how to get the conditional probability of two events. P of A given that B has occurred is P of A intersection B by P of B. I've already made a video on conditional probability. I'm sharing the link in the description box. If you have not watched that video, please watch the video first to understand what is conditional probability. So, conditional probability mass function of the random variable x given that y equal to y is p of x given that y has occurred. This is how to represent, that is p of x equal to x given that y equal to y. This value is fixed now. So x equal to x. So using this definition, p of x equal to x intersection y equal to y divided by this probability, probability of y equal to y. P of A given that B has occurred means intersection of these two. This is A now, this is B. So divided by this value, probability value. Similarly, P of Y given that X has occurred, conditional probability mass function of Y given that X equal to X is this one. In the same way, apply the definition. So this function is called as conditional probability mass function of y given that x equal to x. Now see here, you have to find the conditional probability of x given that y equal to 1. Y equal to 1 you take. So you have to find probability of x given that y equal to 1. So that is the conditional probability. Now how to find this? X can take how many values? Two values, 0 and 1. But y is fixed now. So accordingly, as per this definition, first probability of x equal to 0 given that y equal to 1, and one more is probability of x equal to 1 given that y is also equal to 1. This conditional probability you have to find out. So how to get this conditional probability here? This is equal to x equal to 0 and y equal to 1. That is x equal to 0 intersection y equal to 1 divided by p of y equal to 1. So in this case, probability of x equal to 1 intersection y equal to 1 divided by p of y equal to 1. So x equal to 0 and 1. So 0 comma 1, 0 comma 1, what is the value? 1 by 6 divided by probability y equal to 1. So that means we need the marginal probability. Here we found the marginal probability. When y equal to 1, see what is the value of probability? 1 by 2. So you have to see this value, that is 1 by 2, which is equal to 1 by 3. Final answer is 1 by 3. Similarly, here x equal to 1 and y equal to 1. So 1 comma 1. This value is 2 by 6. So 2 by 6 divided by y equal to 1. Y equal to 1 means again this value half. So 1 by 2, which gives you the conditional probability value 2 by 3. So this is how we find the conditional probability distribution. So now why we need to define this conditional probability distribution for bivariate discrete random variable, that is to check the independence of random variable. Two variables, random variables, are independent if and only if p of x equal to xi intersection y equal to yj is equal to probability of x at xi into probability of y at the point yj. So we had here in the independent events p of a intersection b equal to p of a into p of b means the events are independent. Similarly, the random variables are independent if the value of the random variables at the given points intersection value equal to p of x equal to xi, the product of these two values. And this has to satisfy for each and every value of the random variables x and y. If it satisfies for one or two values, you can't conclude that the random variables are independent. This has to satisfy for every possible pair of the values of random variables x and y. Then only we can say the random variables are independent random variables. I will illustrate this with an example later. Now, let us take few problems to understand the concept. So, we have defined what is bivariate discrete random variable, and its probability distribution has three categories. One is the joint probability mass function, which gives you the combined probability, and another is marginal probability mass function, which gives you individual probability of the random variables x and y. For x, row total; for y, column total. Then the last one is conditional probability mass function, that gives you the probability when one of the variables value is given, which is fixed, and other variables probability you have to find out. So let us illustrate that with this example. So this is the table joint probability distribution of the discrete random variable x, y. You have to find the marginal distributions. So marginal distributions are nothing but x, that is row total, and p of x, that I have to find out. X takes the values 1, 2, 3. Then y and p of y, this is marginal distribution of the random variable y, which takes the value 1, 2. So find the row total here. Zero point 0.1 plus zero point 0.2, zero point 0.3, and zero point 0.1 plus zero point 0.3, 0.4, and this is 0.3. So for x equal to 1, 0.3, 2, 0.4, then for 3 it is 0.3. Then similarly, you have to find out column total. Zero point 0.1 plus zero point 0.1 plus zero point 0.2, zero point 0.4. Then this is 0.6. So it is 0.4 here, 0.6. So both sums are equal to 1. So this is the answer for first one, the marginal distribution. Second one, the conditional distribution of x given that y equal to 1. So here probability of x given that y equal to 1. You have to find the conditional distribution for different values of x. First, p of x equal to 1 given that y equal to 1. So that is p of x equal to 1 intersection y equal to 1 by p of y equal to 1. So which gives you 1, 1. Both x is 1, y is 1 means 0.1 divided by probability of y equal to 1. We get y equal to 1 means this marginal probability, here it comes 0.4 you have to take, which is 1 by 4. Similarly, probably y is fixed given that y equal to 1, which is fixed, don't change. X equal to next value 2 given that y equal to 1. So 2 intersection 1 now. So 2x is 2, y is 1. So corresponding value is 0.1 divided by probability of y equal to 1, which is 0.4. That is also 1 by 4. Next, probability of x equal to 3 given that y equal to 1. 3, x is 3, y is 1. 3, 1 means this value. Okay, so 0.2 divided by probability of y equal to 1 is 0.4, which is 1 by 2. Therefore, the conditional distribution of x given that y equal to 1 is, you have to write it in the tabular form, x and p of x. So x is 1, 2, 3. Corresponding probabilities 1 by 4, 1 by 4, and 1 by 2. So that is, here you can write x given that y equal to 1 to be more specific. This table gives you the conditional distribution of x given that y equal to 1. Next, third question. You have to find out this probability of x plus y less than 4. So joint value should satisfy this condition. What are possible ordered pairs now? 1, comma 1 satisfies, 1 plus 1, 2, less than 4. then 1 comma 2, then 2 comma 1. That's it. 2 comma 2 not possible. 4 less than 4. 3 comma 1 it is also 4 not less than 4. 3 comma 2 5 which is not less than 4. Only these pairs will satisfy. That means probability when x equal to 1 comma y equal to 1, joint probabilities plus all probabilities you have to add to get this value. X equal to 1 y equal to 2, then plus probability x equal to 2 y equal to 1. So see in the table, x equal to 1 y equal to 1 means 0.1 plus x equal to 1 y equal to 2, 1 and y is 2 means 0.2 plus x equal to 2 y equal to 1, 2 1, this value comes 0.1. Add all this you will get 0.4. This is finding the joint probability itself, but condition is given like this. So you have to first find the values of x and y satisfying this condition, then add up all the probabilities to get the final answer. Now here is one more problem. Two discrete random variables x and y have, this is the given probability, joint probability. You have to check are these two random variables independent. So first let me write the joint probability distribution table as per the given data. So x takes the values 0 and 1. 0, 1. Y takes the values 0 and 1. X is 0, y is 0, it is 2 by 9. X is 0, y is 1, 1 by 9. X is equal to 1, y equal to 0, 1 by 9. X1, y is also 1, 5 by 9. Then here you will get P of x, that is row total. Here you will get probability of y, marginal probability. Here you will get, then this is marginal probability of y. So add up all these values. 3 by 9 means 1 by 3. This 6 by 9 means 2 by 3. This is 3 by 9, 1 by 3. 6 by 9, 2 by 3. Both add up to the value 1. This is the joint probability distribution table. Now you have to check these are these events independent. So for the independence of events, p of x intersection y, which is equal to p of x into p of y, should satisfy at each value of the random variable x and y. So first you take p of x equal to 0 and y equal to 0. So that gives you p of x equal to 0, y equal to 0. Probability value is 2 by 9. P of x equal to 0 into p of y equal to 0. At this point, what is the product of these two? So product of these two means p of x at 0 is given by this. You can separately, if you want, you can write the marginal distributions. X is 0, 1, then row sum 1 by 3, 2 by 3, y is 0, 1, column sum is p of y 1 by 3, 2 by 3. Or else you can refer the table directly. If you are getting confused, write separately the marginal distribution of x and y. So p of x equal to 0 means 1 by 3 into p of y equal to 0 means 1 by 3, 1 by 9. So here this is 2 by 9. Are they equal? So it is not equal. You can conclude x and y are not independent random variables. Now you have to define what is joint and marginal distribution functions for the discrete random variable. So in the beginning I have recalled the definition of distribution function. It gives you the sum of all probabilities up to x including x. So joint distribution function is denoted as f of x comma y. There in the one dimensional case just you had capital F of x. Here there are two variables, that's why f of x comma y, which is equal to probability of x less than or equal to x comma y less than or equal to y. That is sum of all probabilities up to x comma y including the point x comma y. Marginal distribution function of x is capital F of x, that is equal to summation over j probability of x less than or equal to x comma y equal to yj. While finding the marginal distribution function for this one variable x, this remain fixed. You have to take sum over columns. That's why summation over j. When you are finding marginal distribution function of y, then it is denoted as f of y, which is equal to summation over I p of x equal to xi comma y less than or equal to y. This is how to denote. I will explain this with the example, which is also denoted as fy of y, and here it is also can fx. Now, one example, considering the probability distribution function given in the previous example, you have to find all these values. So, previous example is this. You have to find out f of 2 comma 2, which is equal to f of x comma y. See, probability of x less than or equal to 2 comma y less than or equal to 2. You have to add the values corresponding to this probability values. X less than or equal to 2 means here x can take the values 1, 2, comma y can take the values 1, 2. So that is probability of, you have to get it one by one. So you will get four possibilities here. X equal to 1, fix x now. Y equal to 1 plus probability of x equal to 1, then y equal to 2, then plus change x now. X equal to 2, y equal to 1 plus x equal to 2, y equal to 2. You have to get the values from the table. 1, 1, that is 0.1 plus 1, 2, 1, 2, 0.2 plus 2, 1, x is 2, y is 1.1 plus 2, 2, x is 2, y is 2, 0.3. So, sum of all these is 0. Now, similarly, second one, f of 3 comma 2 here, this one. In the first problem only the second part f of 3 comma 2. So probability of x is less than or equal to 3, y is less than or equal to 2, means it takes all the values now. So x can take 1, 2, 3, and y can take less than or equal to 2, means 1 and 2. So x is 1, y is 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2. Okay, that is nothing but the entire table. The whole table adds up to 1. So I will directly write 1. You do it once again, that is p of x equal to 1, y equal to 1 plus x equal to 2, y equal to 2, in the same way, but that finally adds up to 1. Now see the second problem. Here we have to find out fx of 3, that is marginal distribution function of x at value 3. So it is p of x less than or equal to 3. So which is equal to x varies from 1 to 3, because x values are 1, 2, 3. Less than or equal to 3 means all these values will satisfy. Therefore, x is equal to 1, 2, 3, and y values you have to take it for all possibilities. So y equal to 1, comma 2, which is equal to, this gives you the sum of all these values, which is nothing but 1. So p of x equal to 1, y equal to 1 plus p of x equal to 1, y equal to 2, then plus p of x equal to 2, y equal to 1, plus so on like this, which is nothing but sum of all these values that adds up to 1. So marginal distribution function of x at the value 3 is equal to 1. Next, third one, fy of 1. You have to find out marginal distribution function of y at 1. So probability of y less than or equal to 1. X I am not specifying, because for all values of x you have to take. So which is equal to y less than or equal to 1. Y values are 1 and 2. Y less than or equal to 1 means only one value satisfies. Y equal to 1. Then for all values of x equal to 1, 2, 3, which is equal to, for marginal distribution function of y, we have condition on y, but x no condition, you have to take all values. So probability of y equal to 1 comma x equal to 1 plus probability of y equal to 1 comma x equal to 2 plus probability of y equal to 1 comma x equal to 3. That is 1, 1, 1, 1, 2, 1, 3. 1 comma 1, y is 1, x is 1. Y is 1, x is 1 means 0.1 plus y is 1, x is 2 means 0.1 plus y value is 1, x equal to 3, 3 1 that is 0.2. So when you add up all these values you will get zero point 0.4. So this is the answer. See, here is a problem. Find joint and marginal distribution functions for the joint probability distribution. This is given here. So first we need the joint distribution function, which is denoted as f of x comma y is equal to p of x less than or equal to x comma y less than or equal to y. Let us find out for all values of x and y. X takes values 0 1, y takes values 0 1. Therefore, first you have to find out f of 0 comma 0, then f of 0 comma 1, then f of 1 comma 0, f of 1 comma 1. So 0 0 0 1 1 0 1 1. These are the possible values. Here f of 0 comma 0 means p of x less than or equal to 0, y less than or equal to 0. This is equal to only one value satisfies 0 equal to 0. So p of x equal to 0, y equal to 0. Which value satisfies x equal to 0, y equal to 0? Probability is 2 by 9. Next here p of x less than or equal to 0, y less than or equal to 1. X less than or equal to 0 means x equal to 0, only one value, x equal to 0. Y less than or equal to 1 means two values possible, 0 and 1. Y equal to 0 and 1. Therefore you have to take the sum of probabilities now. 1 corresponding to 0 0, then with the 0 1. X is 0, y is 0 means 2 by 9 plus x is 0, y is 1 means it is 1 by 9. So answer is 3 by 9. Similarly, I need to get f of 1 0. P of x less than or equal to 1, y less than or equal to 0. X is less than or equal to 1 means x satisfies two values 0 comma 1, and y less than or equal to 0 means only one value, y equal to 0. Now p of x equal to 0 comma y equal to 0 plus add all the probabilities. X equal to 1, x equal to 1 comma y equal to 0. So x is 0, y is 0 means 0 0, which is 2 by 9 plus x is 1, y is 0 means 1 by 9. This is also 3 by 9. Then the last one, f of 1 comma 1 means probability x is less than or equal to 1, y is less than or equal to 1. So that means x takes values 0 comma 1, y takes values 0 comma 1. So accordingly you have x is 0, y is 0 plus probability x is 0, y is 1, four values 0 0 0 1 1 0 1 1, which is nothing but sum of all the probabilities of this table. That grand total must be equal to 1. You can directly write as well. X is 1, y is 0, then probability of x is 1, y is 1. So all these values you have to add up, that gives you the value 1. Therefore, joint distribution function is like this. You can write it in the table. So, joint distribution function f of x comma y in tabular form is like this. So you have here y less than or equal to 0 and y less than or equal to 1. Then here x less than or equal to 0, x less than or equal to 1. So x less than or equal to 0, y less than or equal to 0. That is this first case, we got it as 2 by 9. Next, x less than or equal to 0, y less than or equal to 1. We got it as 3 by 9. X less than or equal to 1, y less than or equal to 0. We got it as 3 by 9. Then x less than or equal to 1, y less than or equal to 1, the value is 1. This is the joint distribution function. Now if you want the marginal distribution function, so first marginal distribution for x, you have to find out marginal distribution function for y. So marginal distribution function of x is denoted like this, fx of x. So now you have values for x as 0 and 1. You have to find them separately. The value marginal distribution function is given by probability of x less than or equal to x. So here first you have fx of 0 because x takes value 0. So probability of x less than or equal to 0, it has only one value, x equal to 0. Probability when x equal to 0, probability when x equal to 0. So y value can change from 0 to 1, any two values. So you need to take this when you have to find out the marginal probability, which is nothing but a row sum for x equal to 0. You can write directly 3 by 9 because we are calculating the row sum corresponding to the value of x equal to 0 row. Fx of 1 equal to probability of x less than or equal to 1, which is equal to probability of x equal to 0 comma 1. So here you have to take sum over all values of y. That is p of x equal to 0, y can be equal to 0 plus p of x equal to 0, y can be equal to 1. Then again x can be equal to 1 means y equal to 0 plus probability of x equal to 1, y equal to 1, which is nothing but the whole probability, sum of all the values, which is equal to 1. Therefore, the distribution function for marginal distribution function for x is denoted as f of x, and in the tabular form it is written like this. Here it is f of x and x less than or equal to 0, x less than or equal to 1. X less than or equal to 0, x less than or equal to 1. For x less than or equal to 0, I got it as 3 by 9. Then for x less than or equal to 1, I got it as 1. Therefore, this is the marginal distribution function for the random variable x. Similarly, you have to find out the marginal distribution function for the random variable y. You do it in the same way. I hope you understood the concept. Thank you for watching.